Hello, good morning. How's everyone doing today? So today is our last lab, actually. Lab 13 will be the last lab of this class. We're able to finish everything before Thanksgiving, and this will be our last class. Your one last week, week 15, you will just have a lab quiz that will be due on Canvas. I will send out announcements to remind you when the quiz day is coming up. But after this lab, it will be everything will be wrapped up. So if you haven't done this already in Canvas, you should already be able to see your estimated grades. So in the grade book, you should see the scores for individual assignments, and then you should also see the overall accumulated grades with every different parts, different weights added. So pre-lab and your worksheet and the quizzes, so they all come together to count for the estimated grade. As your more of the assignments are turned in and graded, that score you see will also be updated. So take a look at that. If you notice anything that doesn't look right, let me know. Also, the late assignments will be given some partial credit. So if you have some pre-labs or old worksheets you did not do and you wanted to make up, you can get 50% of the credit as a partial credit, and all of the late assignment will be due on December 5th. 5th or 6th, it's a Sunday. So take a look at your syllabus. It has a final day there. And I will, after that, all the grades will be final, okay? Do you have any questions about the class and the policies? All right, so this last lab is about, again, for spring. We actually already did similar stuff for part A. So part A, we need to calibrate your spring. The calibration simply give us some idea about, okay, what kind of spring am I using? Does the spring have a big spring constant K, or does it have a small constant K? How much of the friction am I going to experience when I do the oscillation? So we need to calibrate it. So part A, we're just going to get our measurements for K and for the friction. So part A, the data collection process is very similar to our lab 12, that one you already did. So we don't need to look at that part in the video. So for part A, you simply put some weights on your spring. Okay, so put some weights here, and you can see that the weight is equal to the spring force, right? So that your object is in static equilibrium. The weight is pointing down, your spring force pointing up. So mg is equal to k times x. X is the elongation of the spring. So part A, to calibrate it with different mass you add, you're going to measure how much your spring is being stretched. So you're just going to record the final and initial position of your spring, and you can find out how much it's being stretched. So this part is just the same as what we did in lab 12. Okay, so from that measurement, we are going to plot the weight versus the elongation of the spring. And you can see that because you can see according to Hooke's law, this force has to equal to K times the stretch. So you should get a linear relationship. You should fit a straight line through the data, and the slope of that gives you the spring constant. So this will be given, this is the slope. So whatever slope you recorded would tell you what kind of spring you're using, what is spring constant, and then you get a y-intercept. Then that tells you how much a friction is you experience when using this kind of spring. Okay, so the y-intercept will tell you the friction. make sure that when you record the stretch or the elongation of the spring, convert it to meters. Whatever you read on a meter stick, if you read it in terms of centimeters, then you need to divide it by 100 to get meters. So make sure your spring constant is in the unit of newtons per meter. So K should have this kind of unit. All right, so that's just part A. We are obtaining some information about the spring we're using. And then we're ready to do part B. So this lab is about bungee jumping. The idea is if you're doing bungee jumping, you wanted to have a correct calculation to make sure that you're safe. So when you drop the object from a height and then let it go, it's going to stretch the spring and then reach a lowest point and then bounce right back. Okay. So you want to make sure that, okay, where exactly is the lowest point? You know where the lowest point is, you can make sure that you use a correct spring, correct K, and choose a proper height for that jump. Make sure that that lowest point is still well above the ground or whatever surface that is below. Okay. So it is important to be able to calculate this distance D correctly. So in the lab, we show, okay, part B, we're using a spring for this bungee jump. You put a weight here, you lift it up and you let go. And this is the lowest point you can get. So the distance between the initial point and the final point is distance D. So we want to be able to calculate this distance D. So we're going to do this two ways. One way is we can calculate this D using a theoretical method. We will obtain a theoretical value, and then we observe this distance D in the lab. We have a experimental value. So we're going to compare the theoretical value to the experimental value. Okay, so let's take a look at how to calculate D theoretically. So we use a conservation of energy approach to calculate our distance D. The initial energy of your system is simply here. Right now, you're holding and lifting the mass, which means your spring is not stretched. The spring is now simply hanging, which is relaxed. So there is no potential energy from the spring, and your mass is not going anywhere, and the mass has zero velocity, so you have no kinetic energy. The only energy your system had is the gravitational potential energy. Now you're at a height above the lowest point, right? So it's mg times d is your potential energy. When you're at the lowest point, what kind of energy you have? Again, you don't have any kinetic because you have reached the lowest point. You cannot go any further. So at that moment, your mass is momentarily have zero velocity, so zero kinetic energy. And zero potential, because we can set this as our reference point, where we call the potential energy is simply zero at that point. Okay, so zero potential. And the only energy you have is the energy stored in the spring. Okay, energy stored in the spring. So this is, let's go to our pre-lecture to see, to write out this calculation. So the energy stored in the spring, we have talked about the energy associated stored in the spring. Another way to look at this is how much work done by the spring. Right? So in this case, the work done by the spring is the spring force times the displacement. I'm using the integral definition because my force is no longer a constant. So you can see I cannot simply say force times total displacement, because you can see this force is not a constant. This force depends on your position. So you need to use the integration method to calculate your work. So my force is a spring force. That is the Hooke's law, Kx plus the friction. So that is my force. So from here, we can calculate final energy stored in the spring. Okay. So the first term, integral of x dx becomes 1/2 x squared, the lower to upper limit. The second part is F0 times x from 0 to d. Okay, so my final energy is 1/2 k d squared plus F0 d. Okay, so use a conservation of energy approach. Conservation of energy approach tells me that, well, when there's no energy transfer, your final energy is equal to your initial energy, right? There is no energy input or output. So in this case, these two has to be equal, which means 1/2 k d squared plus F0 d is equal to your initial energy, which is mgd, that the gravitational potential energy you have. Okay, so I'm going to solve for d. I'm going to cancel d. I have this. So my d is equal to mg minus F0 times 2 divided by spring constant k. So this is my d. Okay, so that's the theoretical method. Okay, so you plug in mg, you plug in your friction, you plug in your spring constant, and you can get your distance. So in our lab, from the theoretical method, okay, so you get d is 2mg minus F0 over k. So the weight that you used is 4.41 newtons. So that's already decided for us. So we use a particular kind of mass so that the weight is this much. And your F0 is the y-intercept from your part A, the calibration process. So whatever in y-intercept you obtained, that is your F0. Your K was the slope from the calibration process. So you should have already measured these two from part A. And plug it into this equation, you will get a theoretical value for how big of the fall that you're expecting. Okay, we're going to compare this to what do you actually measure in the lab. We actually even measure in the lab is easy, right? Because we just have to set up the meter stick and record what the initial position is and see what is the lowest position, and we can figure out what the distance of the fall is. So let's take a look at that part in the lab. So part A,
as your life mate.
Part A is a calibration process. We're not going to look at the data, but we're going to take a look at your initial position. Okay, because for part B, you're letting go of the spring at the same initial position. So they're not going to show the initial position again. They showed it in part A. So we'll take a look at that. So this is your initial length. You will record that. That's for part A. Also, that's the initial position for part B. So I recommend using the Hooke. Don't use anywhere of the spring because the spring will change positions. Use the lowest part that the Hooke. It looks like it's at 165.2. Sorry, 165.7. Somewhere around that centimeters. That is your initial length. If I'm using the bottom of the Hooke. Now you can pick a different points on the Hooke, but just be consistent. Okay, so part A, simply they're adding different masses and you record where the bottom of the Hooke is at different places. I do want to remind you that the meter stick is put sort of, instead of top down, is bottom up. So you can see that your final position is actually reads at a smaller value than your initial. So your initial was 165.6, 165.7 or something like that. And this final position you can see is a 154.8, for example. So you will need to look at the difference between them to find out the elongation. So you need to use your initial minus the final to get a positive value, just because the meter stick is set up from bottom up. Okay, all right, so let's go to part B, where they have the fall. The initial position is the same. They're not going to show again. And they're going to show you the filming of 3 different videos. So you have to do this multiple times, 3 trials, and take the average of the distance you measured. So you can focus on one of the film at a time and then go back and play for the other film. So right now I was focusing on film 1. Okay, so I pause it when I think it's right at the lowest point of the spray. So I may have to do this multiple times. You may have to do this multiple times. If you didn't get exactly lowest point, I'm gonna just rewind and do it again. So looks like right now the final position according to my video 1 give me, if you can't see this very well, you can take a ruler and kind of line them up and allows you to read it a little bit better. So it looks like this is around 53.7 centimeters. So that's the lowest point for trial 1. So you record that as a final position and you do this 3 trials, and you will do video 2. So you can see I need to go back to do my video 2 and just to get that lowest position. If you feel like, okay, I have went over a little, again, you can rewind and do that again. So film 3 is later, they give you another film 3. And you take the average of all of 3 and you get a average distance of the fall using the experimental method, right? This initial position should have already been recorded from part A, and you will read 3 different final positions and take the average for the distance of the fall. Okay, so the experimental method is quite straightforward, right? You just simply observe how far did it fall, and don't forget to compare that to your theoretical method to see if they match. Part C is exact the same lab. Instead of using a spring, we're using a bungee cord. Okay, so first of all, we are checking the how the bungee cord extend when you add different masses. So as you add more and more masses, you wanted to record the elongation of the bungee cord. And as you will discover, that is actually not a linear function. So as you fit the weight that you added and the stretch of the cord, you'll see that it does not fit into a linear function. So you'll record this table and plot your graph and show that it's not linear. Okay, so it will look like a curve. Now you have the option to draw it by hand. I strongly recommend using computer. It will be much more difficult to do it by hand. But if you do draw it by hand, then to fit a curve, you simply draw a smooth line, smooth curve that connects the points as best as you could. Okay, if you were doing this using a computer, you have to choose the correct functions and choose a polynomial fit instead of linear fit. It's not a linear function. Then choose the order 6. And they should give you a equation that's showing exactly how the force relate to the stretch. So you will not get exact same value as this, but this could serve as sort of a guide of what kind of function you're looking to get. All right. So the first part is simply to check the linearity and you realize it's not linear, it's a curve. And then we're going to do the bungee drop, right? We're going to do bungee jump. The actual data sheet will require the required part that you record the experimental value D, and you're done. The extra bonus part is if you can figure out this distance D using a theoretical method, because that part is a little bit complicated. We will not require it. It will be a bonus points if you do complete it. And I'll talk about how to do it later. So to measure the distance D experimentally is very much the same as before. You record the initial position and the final position and do it 3 times. So part C, let's look at that really quick. With the bungee jump using an actual cord. So record the initial length, right? Okay, so somewhere around 126 or 127 centimeters, that's your initial length. And as you add more and more grams, you can see your bungee cord is at different final position. So this will give you what the data that you need for check the linearity table. And then you'll eventually just let it do a bungee drop. And again, there are 3 different trials. Pause when you need to. So somewhere around 110 centimeters seems to be the final position. I'm just doing it very, casually. You gotta play this a few times, make sure that you are recording the final position and read it more carefully. Okay, so that's the experimental method. Just the same as before, as you can see, it's not hard at all to do this experimentally. You can get this value D. All right, now, if you wanted to stop there, then your job is done. That's all is required. The theoretical part is a little bit complicated, but it's doable. I will explain it now. So if you do want to get extra bonus points, you can do the last bit is to find this distance D to fall using a theoretical method. So you might wonder, well, what's the big deal about this? Didn't we find the distance D theoretically with the spray? So we should be able to do the same thing for the bungee cord, right? Yes, so the method is the same. The only part that make it more complicated now is the force is not a clean linear relationship. Now remember, what did we do previously? We said, okay, initial velocity, the initial energy is mgd, right? The final energy is kx plus friction dx. We know how to integrate this, and we set them equal to each other, and we found our d. Now the only thing that make it more complicated, because now your force in the bungee cord is not a linear relationship. So we're simply just going to substitute this to be a correct relation. So what is the force here in the bungee cord? Okay, so we have to go back to our data, see, okay, our computer has given us an equation, right? The computer has given us this particular equation. And what I want to calculate is this potential energy. So potential energy is the integral of the force dx. So this is the area under the curve. If you were to do this by hand, you can count the area under the curve by count how many little grids is under the curve. So it's hard, but it's doable. You can count, okay, how many little grids is under this. You have to count how many grids, and that tells you the area under the curve for the potential energy, right? You count all the different U's for different positions, and you plot a new graph. See, that is hard. We can also use our computer. That is a recommended method to calculate this potential energy. All right, so how do we do that? Here we already found this function. Y is all of this. So we just simply tell our computer to, okay, we can just integrate this to get this function. So for example, the first data is negative 556890 x to the power of 6. That's the first term. We know when we integrate this, right, we get negative 556890 divided by 7 times x to the power of 7. And you can insert your x value of that particular point. Whatever your x value was, remember what was your x? Your x was recorded as the elongation. Okay, so record using whatever x there, that can give you the integral of this entire potential energy stored in the spring. So you have many terms, so you need to add all of them together. So that will give you a new curve. Once you have a new curve, and this is simply the MGH. This is a straight line. These two will overlap. And when they overlap, which means that you have set one equation to another. This is tell you MGH, initial energy is equal to your final energy. And where they meet is exactly where your D is. That is your drop. Okay, so let me show you that process by open up my Excel sheet, and I can show you how to do it. Okay, so let's take a look at, okay, when you're writing down, recording your data. So here for the bungee cord, you recorded an initial length, you record a final length. So you all have different data than me because you read it slightly different than me, right? Okay, so you will have the elongation of your bungee cord at different masses. Okay, so for different mass, convert the grams to kilograms multiplied by 9.8. You get all the different weights in newtons. That's your Y value. Your X value is your initial length minus your final length. That is your elongation. Divide that by 100, you get the elongation in meters. So what you wanted to plot is your X versus your Y. And be very careful, you need to add a 0, 0 point. So that means when you are at 0 stretch, when you add a 0 mass, you should add 0 stretch. You need to include that 0, 0 point in your graph to make sure that it fits correctly. So you will insert the chart. You want to choose a scatter plot to make it plotted for you. Okay, so they will give you a graph. Okay, then highlight the graph. You want to be able to add a line. You will choose the polynomial fit and make the order of 6. That seems to give you, we choose 6 because that seems to give us the best fit. Okay, then you also make sure that you have the equations that you need on the graph. Okay, so that is your first part. Is a linearity. It's not, it is a curve. And then to find the bungee cord, to find the distance of the fall, theoretically, you need to do the second part. Okay, so for all of these different points, you can see we need to calculate the integral. Okay, so how do we tell the computer to give us the integral? Well, we know that this function is y is equal to some constant times x to the power 6 plus some other constants, x to the power of 5. Okay, so I'm just going to write out the function, the formula in my Excel sheet. I will say, okay, this integral is this constant. You can see that's the first constant divided by 7 because the integration of x6 is 1 over 7 x to the power of 7, right? Multiplied by the x value to the power of 7. The next constant divided by 6 multiplied by the x value to the power of 6 because this was the x to the power of 5. Until you get to the last one is a constant. The integral of the constant is a constant times your x value. So every X value, I will get a different area under the curve. So this is just, you can enter into your Excel. And whenever you have X, use that cell to represent it. And you can just drag it down and that will fill out the integral for you. So you can see now I'm able to get my new curve, which is plotting different stretches corresponding to different integrals of that X that represent the energy stored in the spring. So I'm going to plot the X versus the integral of the X that give me the energy stored in the spring, but I also need to plot the gravitational potential energy. So this part is potential energy of the spring. This part is the potential energy of gravitational potential energy. So when these two energies equal to each other, that where they equal, where they intercept, that tells me what is the, at what distance d is the drop, okay? So when you need to plot two different curves, you highlight all of them. First column is your X value. The next two columns are your Y values. Highlight all of them and you will insert this chart again. So they will plot both of these charts on the same graph and you'll give it individual fit. Okay, so this blue one was your new curve, that's your potential energy. You do a polynomial second order fit, that will work. And this would be your potential gravitational potential energy. That is a linear line. So that's just MGH. So that's a linear line. So you can see that they overlap on your graph. Here, right there, right here, they overlap, and record exactly where they overlap. So they overlap on the x-axis somewhere between, looks like it's halfway between 0.2 and 0.25. Okay. You could format your axes to be a little bit more accurate, so that you can read it a little bit better. So for example, if I change my scale, I can read this a little bit better. Just change it, whichever makes sense to you. Seems so this seems better for me. So okay, so it looks like it's right here, halfway between 0.2 and 0.24. Okay, so that would be your distance d. And you compare that with the experimental value that you get. Okay, so you can see whether they agree with each other or not. So that's the last bit. The last bit is a little more complicated, so we do not require it. But if you do the last part, you will get a bonus point for the worksheet. So that concludes all of our labs for this one. Part A, calibration. Part B, a bungee drop using a spring. Part C is a bungee jump using a bungee cord. All right. So at this point, do you have any questions? Any questions so far? Okay. If you do think of any questions that you run into while you're doing the worksheet, feel free to email me. That concludes everything we need to do for 1510 labs. I want to appreciate and thank you everyone for those of you who always attend the class and meet with us synchronously every week. and for appreciate those who take data together with me. And I hope that you have a good rest of your semester. If you do have any more questions about the class portal policy and the grades, feel free to email me anytime between now and the end of the semester. All right, so I will still be in office hours for the rest of your week, the semester. So if you have any questions, stop by office hours or email me. And best wishes on your finals. And bye, everyone.
Thank you, Professor.
Bye.
Take care, Professor.
Thank you all. Bye-bye, everyone.